Okay, so our last section for the week, if you're following along in the packet, it's 5.6. You can double check, but I'm pretty sure it's 5.6. If you're looking in your book, it's 8.5, just last part. Okay, so what we're looking at is vectors in space. Okay, what space means is three-dimensional space. So everything that we've been doing up until now has been in that area. Okay, depending on how you see this, if you look at that as like the bottom of a box, like you're looking into the corner of a box, this side is coming up this way, and this side would be like the back of the box in this area here. This is the bottom. So now what we're doing is we're introducing a z-axis, which is going to come up off the bottom of the box. Okay, so z-axis gives you a third dimension. Now, there's different ways you can do the z-axis, but the idea is this is called a right-handed coordinate system. And your book explains what that means. So if your index finger points in the direction of the positive x-axis, and your middle finger points in the direction of the positive y-axis, then your thumb will point in the direction of the positive z-axis. So in this example, it's kind of hard to look 3D, but x would be kind of on the bottom, y would be towards the door, z is up. X, Y, Z. So that tells you which way the z-axis points. If it was left-handed, what would happen is if you line up X and Y, your thumbs point in the opposite directions if you use left hand. So that would make the z-axis go the other way. This is called a right-handed coordinate system. Okay. So any questions on how you can figure out which way is which? Index finger, paw pointed in the direction of X, point your middle finger in the direction of Y, your thumb will automatically give you Z. And all those axes are perpendicular. X and Y are perpendicular, Y and Z and X. They're all perpendicular to each other. All right. So, in 2D, okay, what I'm going to do for a lot of the formulas today is I'm going to put recall, remind you what we did in 2D, and then we'll extend it to 3D. So you don't really have to write down all the 2D stuff again, unless you want to, but it's already in your notes. All right. So in 2D, we had an X component and a Y component. A is the X, B is the Y component. So A tells you how far to move along the x-axis, B tells you how far to move along the y-axis. Okay? And then I and J, those were unit vectors. Now when we extend it to 3D, we're going to need one more unit vector. Anyone have a guess what we're going to call our third unit vector? K. So this is a unit vector, I, J, K. So the third unit vector is K. So remember, these I's and J's, they're all 1 unit long. I showed you an example kind of like this, where we stacked a bunch of them together. People remember doing that one? We stack them together. That's how we build unit vector notation. Well, now you're stacking them in 3D. So maybe you'd go over, up, and then out towards you a certain amount. Okay, as far as sketching it, you don't have to worry about it. You just have to know that K is the unit vector along the z-axis. I is the unit vector along the x. J is the unit vector along the y. Okay, now if you were to write this in the other notation we have, you could also do it that way. You use the angle brackets. Inside the angle brackets before, we only had 2 numbers. The first number was representing the x-axis movement. The second number represented y-axis. Well, now our third number represents to the z-axis. Okay. Any question on that? Okay, so remember, A, B, and C are the components of the vector. Okay, the component is how much you move on each axis to get from the initial point to the terminal point. Okay, so just like in 2D, if you have a vector that has its initial point at the origin, it's called a position vector. There's no change in that definition from 2D to 3D. So you already have that in your notes. So a vector that has its initial point at the origin is called a position vector. Okay, I'm going to come back to this. I had skipped over it. It's fine. I'll finish up position vector and then I'll come back to distance. Okay, so in 2D, that's how you found a position vector. Okay, I think I gave you that on Monday. You subtract the x's, comma, subtract the y's. Make sure you put angle brackets around it. What were those x's and y's? They were the coordinates for the initial point and the terminal point. Okay, we always subtract terminal minus initial. Okay, and you guys did that in Monday night's homework. Okay. Now in 3D. We're no longer going to have a coordinate that just has an x and a y value. Our coordinates in 3D are now going to also have a z value. So in 2D, you call those ordered pairs. In 3D, we call those ordered triples. So your initial point would have an x, a y, and a z value. And your terminal point would have an x, a y, and a z value. Okay, does anyone have a guess what how the formula for a position vector in 3D is going to change from the one that I gave you on Monday that was in 2D? Ezekiel?
You have like another column, z, 2 minus z1.
Yeah, all you're going to do is you got to do one more calculation. In 3D, you still have to find the difference between the x's. You still have to find the difference between the y's. But now, you also have to do the difference between the z's. That's pretty much how all the formulas work today in 3D. You're just looking at the pattern you had before and extending it one more time for the z-axis. Okay, that's why I said if you make a reference sheet, I wouldn't put all the formulas for 2D and then do all the ones for 3D separate. They're the same formulas. Just put the 3D ones. And if you don't need the z part, just block it. Ignore it. Don't use it. Okay, so we'll try an example of finding a position vector, then I'll go back to the page that I skipped on distance. Okay, so let's find the position vector between P1 and P2. So P1 is negative 1, 2, 3. P2 is 4, 6, 2. Okay, and what's going to be the first two numbers I subtract when I find the position vector?
4 minus negative 1.
Yep. So we'll come back and do that out. We got 4 minus negative 1. Matt, what about the next two numbers?
6 minus 2.
Yep. 6 minus 2. And if this was a 2D problem, you'd be done right there. But since it's 3D, we got one more step. Mike, what's my last two numbers I have to subtract?
2 minus 3.
2 minus 3. Yep. Okay. And now just do that out. 4 minus negative 1. 6 minus 2. 2 minus 3. Okay. So that's how you could write the answer using the angle bracket notation. How could I write that using ij's and k's? Yep, Nina?
5i plus 4j minus k.
Yep. So you should be able to write it either way. 5i plus 4j minus k, or the way we just had it up above. Any questions on that? Okay, so everyone's good with finding position vector in 3D? Okay, so let's take a step back before we continue on with more stuff with vectors and talk about distance in 3D. So in 2D, that's your distance formula. You subtract your 2x coordinates, you square it. You subtract your 2y coordinates, you square it. You add them up and take the square root. What formula is that really? Distance formula. Yeah?
Just like a Pythagorean theorem.
Yeah, it's just the Pythagorean theorem. Square plus square, take the square root. So in 3D, if I ask you to find the distance between 2 points, we can pretty much do the same thing. We can do the Pythagorean theorem in 3D. So to extend what I have here to 3D, what do you think I would need to put on the end of the formula?
The same thing in those two brackets, except z.
Yeah, just a z2 minus z1 squared. Okay, so just extend it for the z's. So the difference in the x's squared plus the difference in the y's squared plus the difference in the z's squared. And then take the square root of all that. So this is a little different than what we did before because the calculation you guys did before this was to find a vector. This calculation is not going to give you a vector. It's going to give you a number. It's going to give you a distance. How far apart are two things. This is the only calculation we do today that doesn't involve vectors at all. It involves a coordinate and another coordinate. That's why I wanted to do this one first, but it doesn't really matter. Okay, but there will be one of these on the test. I'll give you 2 coordinates, just like that, and say find the distance between them. Okay, so let's set it up. Okay, so we've got square root of, and it's a good idea here because there's a lot of symbols, a lot of parentheses, subtractions, and squaring. I would just set it all up and leave room to plug everything in. And hopefully by setting it all up first, you don't forget to square something, or you put all the symbols in the right spots. We're not even thinking about numbers yet. Just the template. Okay, now let's fill it in. So Hannah, what are going to be the first 2 numbers I plug into that set of parentheses?
x2 minus x1.
x2 minus x1, which in our case will be?
4 minus 1. Minus negative 1.
Yes. So it's 4 minus negative 1, which will become plus 1. Okay. Brandon, what are the next 2 that I'm going to subtract?
Negative 2,
Yep.
3.
Negative 2 minus 3. And then the last one, 5 minus 2. Okay, so let's do that out. Wyatt, what's 4 plus 1?
0.
4 plus 1?
Oh, 4 plus 1, my bad.
Yeah.
Squared. 9.
4 plus 1.
5.
5? And then square it?
25.
Okay, make me nervous. I'll do the next one because you get negatives. Negative 2 minus 3 is negative 5. When you square it, you still get 25. Maybe you were doing the last one. What's 5 minus 2? Your favorite number?
3.
3. There you go. 3 squared, 9. All right. So just add it up. There's not really much we can do. Square root of 59. Okay. All the rules with square roots still apply. If you can reduce it, go ahead. Other than that, just leave it the way it is. Okay. Any questions on that one? Okay, so again, only formula today that doesn't involve vectors at all. Just 2 3-dimensional coordinates. Then we did our first calculation for vectors, finding the position vector. We did that one. Okay, so now we're going to look at some other formulas. Okay, I'm going to give you the formulas for adding, subtracting, scaling, and finding the magnitude in 3D.
How many questions are on this test?
Like 17 or 18?
Are they all like 3 parts like homework last night?
No.
Okay, good. That would be a long test.
I don't think people will have an issue finishing on average. Average. All right, so if we wanted to add 2 vectors together, okay, I've got vector v, vector w. Each vector has an x, a y, and a z component. In a real problem, it would be something like that. They would all be numbers. And to add these up, in 2D, we added the x's, then we added the y's. What am I going to have to put on the end there to do it in 3D? Z1 if you're adding, plus Z2 if you're subtracting, minus. So I just combined it all into the same formula for adding and subtracting. We either add the x's, add the y's, add the z's, or subtract the x's, subtract the y's, subtract the z's. This is taking the place of doing anything with drawing. Okay, you can absolutely sketch it in 3D. A little easier if you do it like on a computer rather than by hand, because then you can sketch it in 3D and you can kind of rotate it and look at it from different angles. Which on paper, that's kind of hard to do. Okay, the second one. Does anybody remember what we call alpha? It's a number, but what it does to the vector kind of tells you its name. Scaling. It scales it. So in 2D, if you wanted to scale the vector v, you multiply the x component by the scalar, multiply the y component by the scalar, and what am I going to have to do to make this 3D? Multiply the z component by the scalar. Okay, so that's why I said today it's pretty much a review. Okay, it's kind of going over everything we did in 2D again. Okay, and magnitude. Okay, to find the magnitude of a vector in 3D, it was in 2D, it was the square root of the x value squared plus the y value squared, and if it was 2D, you'd be done. Colleen, what am I going to have to put on the end of that to turn that into a 3D formula?
Sorry, what?
What do I have to put on the end of that to make it 3D?
Z1 squared.
Z1 squared. So there's how you find a magnitude in 3D. Okay. Any questions on that? I'll give you some numbers and we'll go through each of those formulas. Okay, I've given you the vectors in unit vector form. That means it has an ij and a k. But we'll practice writing the answer with ij and k and with the angle brackets. Okay, so let's start with v plus w. So think of it as combining like terms. Combine the i's, combine the j's, combine the k's. Okay, how do you combine them? Look at what they want you to do. They want you to add them. Okay. So AJ, if I add those up, what would be my I component? 5. Yep, exactly. 5i. Curtis, my j component?
That'd be negative 1j.
Yep, so you can put negative 1j, that's perfect, or you could just put negative j, same thing.
All right.
And Josh, what about my k?
3.
3k. Okay, so there's your answer as a unit vector. Let's write it with the angle brackets. Braden, can you tell me that same answer?
So it would just be 5, negative 1, and 3.
Perfect. Yep. 5, negative 1, 3. Any question on how we got the answer or how to write it with the angle brackets rather than ijk? Okay, so that's adding. Let's look at magnitude. So magnitude is an operation that you don't need the other vector. You're not using w at all, just v. Okay, when I'm finding magnitude, what's the first thing I want to write down so I don't forget to do this in the end? Yeah, put the square root down so we don't forget it. And Andrew, could you fill in the rest of the formula to find the magnitude of v?
25 plus 1 plus 9.
Can you explain how you're getting those numbers?
I did 5 squared, and then negative 1 squared, and then 3 squared. But I just had them.
Okay, so you were finding the magnitude of this, which we could have asked for, but I didn't.
Just v.
Yeah, just v. You don't have to find the magnitude of v plus w.
So 4 plus 9 plus 4.
Yes. 2 squared plus 3 squared plus negative 2 squared. So 4 plus 9 plus 4. And what did you say that adds up to?
Adds up to 17.
17. And that's it. That's your magnitude. Square root of 17. Is that a number or a vector?
Number.
It's just a number. Okay. Vectors have ij's and k's or angle brackets. Square root of 17 doesn't have that. That's just a number. Okay. And subtraction is kind of the same, so I'm going to skip subtraction. Let's do a scalar product. 3w. So, Mallory, could you tell me what 3w would come out to? Yep, we get 9i minus 12j plus 15k. Yep, perfect. Any questions on how you would write that with the angle brackets? Okay. Any questions on adding, subtracting, scaling, or magnitude in 3D? All right. So next thing. So now we're up to where we were yesterday. Okay, when you learned dot product in 3D, or in 2D, I'm going to show it to you in 3D. Okay, to do a dot product in 3D, the first thing you need is 2 3-dimensional vectors. V and W are my vectors. X1, Y1, Z1 are the components of the first vector. X2, Y2, Z2, those would be the numbers in the second vector. Okay, to find the dot product. In 2D, we multiplied the x's together, plus we multiplied the y's together. And Casey, what do you think I'm going to have to do to extend the definition of dot product to 3 dimensions?
Multiply z2
Z1 and Z2.
Multiply Z1 and Z2 and add that as well. So there's your calculation for the dot product in 3D. Caitlin, when I do a dot product, what kind of answer do I get?
You're gonna get numbers.
A numbers, exactly. I'm going to get a number. Okay, dot product does not give you a vector. It gives you a number. It did in 2D, it still does in 3D. And what did we use dot product for yesterday? Like we practiced finding it, but then we used the dot product as part of another formula. Yep.
We use that as the numerator and
Yep, we used it as the numerator
to find the angle.
exactly to find the angle. So eventually we're going to do the same thing here. We're going to use it as the numerator to find the angle. But first, let's just practice finding a dot product just by itself. In fact, what I'll do next is I'll take these two vectors and find the angle between them. Since we've already have done the dot product in this part, that'll save us time in the next part, if we use the same problem. Okay, so let's find the dot product. So let's just set it up. Okay, Ezekiel, can you tell me first two numbers I multiply? To do V dot W.
2 and 5.
2 and 5, yep. Ian, the next two?
-3 and 3.
-3 and 3. And Matt, last two?
6 and -1.
6 and -1. Now, is the dot product commutative?
Yeah.
Yes. If you switch the order and do W dot V, you would have gotten the same answer. So had Ezekiel said 5 and 2 instead of 2 and 5, technically it's the same answer. All right, so we get 10 minus, actually I'll just do it like this, 10 minus 9 minus 6. Okay, what's 10 minus 9 minus 6?
-5.
-5. And that is the dot product. Any question on how to do a dot product in 3D? Okay, so this test has more questions than usual, but I don't think this kind of question should take you very long. Okay, all the questions are pretty quick, except the word problem. That takes a little long. Okay, so next step, let's look at how we find an angle in 3D.
How many word problems are in the test?
1. Yep, 1. Okay, so to find an angle in 3D, first thing you need, two vectors in 3D. I'm using the same thing I've been using all along. Whether you call the vectors V and W or P and Q or whatever you call them, the letter doesn't matter. Okay, what's important is the formula. And that's the formula to find the angle between two vectors in 3D. What's the difference between that formula and the one we had yesterday as far as how it looks?
The same.
It's the same. The difference is it's a three-dimensional dot product divided by a three-dimensional magnitude times another three-dimensional magnitude, or a magnitude calculated from a 3D vector. That's a better way to say it. So a three-dimensional dot product divided by the product of two magnitudes calculated from 3D vectors. You guys have done 3D dot product. You've done finding the magnitude of a 3D vector. So you've already done all the calculations that are part of it. So now we'll look at an example. Yep.
Is there any reason, because like I noticed on like the other ones you took the other day, you like change your variable to like U instead of W. Does it not matter?
No, the variable doesn't matter. No. If you want to put W instead of U, that's fine. Okay, so let's find the angle between U and V. And I think I used the same ones we had up above. 2, -3, 6, and 5, 3, -1. So that'll save us a little time because we already know the dot product. What was the dot product that we just got? -5. Okay, now I need the magnitude of u and the magnitude of v. Dave, can you tell me to find the magnitude? First thing I should write down so I don't forget it. Something we need to put, well, you know what, you just tell me how to find the magnitude and we'll just see if you get everything from there. How do you find the magnitude of u?
By the factors. Maybe something else, but I don't know.
Not sure. Anyone help him out to find the magnitude of u? Yeah.
Square root of, do you want me to say the numbers or
You can square them as you go if you want.
4 plus 9 plus 36.
Yep. So she did the square root of 2 squared plus -3 squared plus 6 squared. So what I was getting at, Dave, was what you put first is the square root symbol. What's 4 plus 9 plus 36? Square root of 49, which is how much? 7. So we got a nice answer for the magnitude. Doesn't really matter because we're just going to let the calculator figure it out anyway, but we got a nice number. And the magnitude of v. Colin, can you tell me how to set up my formula to find the magnitude of v?
It'd be the square root of 25 plus 9 minus k.
Yeah, 25
Minus 1.
plus 9 plus 1. So it's the square root of 35. Can't really do anything with it, so we'll just leave it.
Wait, never mind.
No, I think he's good. Okay. Any questions on that? Okay, now we've got the 3 parts we need. Let's fill them into the formula and get our angle. Curtis, can you remind me what trig function do I use on the left side to find the angle? No, not sine. Cosine. It's cosine. Cosine of the angle equals what goes in the top?
-5.
Dot product goes in the top. And in the bottom?
7 squared to 35.
7 square roots of 35. And now we're trying to get rid of cosine, so inverse cosine. All right, so second inverse cosine. If you're going to type it all in at once, use parentheses like I'm showing you right now. -5 divided by, open a parenthesis for the denominator, type in the denominator, close the denominator, close the inverse cosine. Could you get away without the parentheses in there? I think you could this time if you didn't put it around the 7 and the square root 35. But if you put it like that, I guarantee you will get it right. And it's 96.93. So if I went one more step and said, are these parallel, perpendicular, or neither? Neither. They're close to perpendicular, not quite. What's the other word for perpendicular, if you see that on the test? Orthogonal. Yep. Orthogonal.
So there's going to be vocab on there?
Only in terms of the directions, we'll say, are the following vectors orthogonal? So I won't answer if you're like, I don't remember what orthogonal means, then I won't tell you. So you just have to know what that means in order to answer the question. All right. So the last thing, I'm going to mention it, kind of explain it a little bit, but we're not really going to get into calculations with it. Okay. And it's what's called the cross product. Okay. I basically just want you to be aware of that this thing exists. Okay. So the cross product is a second way to multiply vectors. What was the first way called? What kind of product? Dot product. And with dot product, we learned it was commutative. V dot W equals W dot D. Okay. This is the reason we don't say times. or multiply when we talk about vectors. Because if you said to somebody that knows anything about vectors, I want you to multiply vector v times vector w, they wouldn't know what to do. If you just say multiply, you have to be more specific. Multiply them with a dot or cross, which way? I'm not really going to get into how to do it with a cross. I'm just want you to know that it exists. The reason we didn't look at it in 2D is because you can't. There's no such thing as a cross product in 2D. Basically, what happens is if you give me two vectors and I find the cross product between them, the answer is a vector. That's different than a dot product. The dot product, the answer was a number. The cross product, the answer is a vector. But it's not just a random vector. It's a very special vector. If you give me two vectors and I find the cross product, the answer will be a vector that's perpendicular to both of the original. So if you had two vectors and you want to find a third one that's perpendicular to both, that's what the cross product does. And if you're wondering, well, how could you use that? Well, if you were in a plane and the plane could shoot out, let's say, shoot out two lasers that hit the ground, the plane could find the cross product between the two lasers that went out from the plane, and it would tell you which way is up. So in a computer, you'd be able to figure out which way is up. You might think it's always easy to know which way is up, but when you're flying, it can be very easy. You can get disoriented. If it's nighttime, you might do the wrong thing and you might go down instead of up. People have crashed planes before doing stuff like that. So that's an example of how a computer could use a cross product to find a perpendicular direction to the ground. So I tried to just explain to you an application into flying. There's other applications with physics and geometry. Calculus, ton of stuff in calculus with cross product. But not really a calculation we're going to get into. The symbol for it, what you would probably guess, it's a little cross. That means V cross W. This means V dot W. And when you find a cross product, you cannot switch the order. Well, you can, but you won't get the same answer. V cross W is not the same as W cross V. So cross product is not commutative. And if I were going to go through an example, I would show you that. Okay. So any questions on just that idea? What a cross product gives you, don't have to worry about how to calculate it though. Okay. So that finishes up everything for this week. So homework tonight, it's in your packet. So it's 15, 17, 29 to 35, just the odds. 41, 43, 51. Okay, tomorrow we'll have our tests. It's about 17 or 18 questions, one word problem. And it's pretty much in order of the stuff we learned. The 2D stuff will be first, 3D stuff will be at the end. Okay, any questions about the test tomorrow? If you are at skills, is anyone at skills tomorrow? Okay, so if you're at skills, you have until April 6th. You have until April 6th to take the test. Anytime between now and April 6th. Before school, after school, on Wednesday, or during the study.